Yesterday we talked about some of the variables related with different states of matter, and today we're going to compare those variables. So let's just review real quick the three that we're going to talk about. The first one is pressure, and the symbol for pressure in the equations will be just a P. And there's a whole lot of units for pressure, but the main three that you'll see for this chapter is going to be ATM, which stands for atmospheres, millimeters of mercury, and torr. The next variable is volume, which is the letter V in the equations. And this will either be in liters or milliliters. And then the last one is temperature. And we don't use Fahrenheit in science, we usually use Celsius, that's what our thermometers are in. But for this chapter we actually can't use Celsius, we'll have to convert those to Kelvin. And I'll explain why in just a few minutes. But the conversion for Kelvin is really easy, we talked about it yesterday. All you do is add 273 to the Celsius temperature and you'll have Kelvin. And you actually don't even need to memorize that, it's in your reference packet. The main thing for these problems is to make sure your units match. So for instance, if you start with your pressure in ATM, it needs to end in ATM as well. So if you started in ATM and ended in torr, you'll get the wrong answer. So just make sure that your units match. STP, if they ever say that in a question, stands for standard temperature and pressure. And so you don't need to memorize these. These are all in your reference packet. If they said, for example, that something's at standard pressure in torr, you would have to know that it's 760, but you just have to look it up in your reference packet. So the first relationship we're going to do is when you hold constant temperature. So you have to hold one of the three variables constant in order to compare the other two. So in this case we're going to keep temperature the same, it's not going to change at all. When you keep temperature the same, as you increase the pressure on something, the volume will decrease. And that means that they're inversely related, and inverse is the same thing as indirect. So whatever happens to one, the opposite thing will happen to the other one. So for example, if you press on the outside of a balloon and the balloon shrinks, you can see that as you increase the pressure, the volume is going to decrease. The equation for this is P1V1 equals P2V2. So 1 and 2 stand for the initial conditions and the final conditions. P is pressure and V is volume. So all you have to do for these word problems is label the information that you're given and then plug it into the equation. And then it's just a matter of basic algebra to rearrange the equation. So if you look at this first one, it looks overwhelming because it looks like a long paragraph, but it's really not bad at all. As you read the question, every time you get to a number, just go ahead and label what it's telling you. So the 500 milliliters is telling us volume, milliliters is volume. So on top of that, in your problem, I want you to put a V1. It says that it's at 1 ATM, so that's your pressure, so that's P1. Go ahead and label that as P1. And it says it's at constant temperature, which tells us that we can use this equation. The pressure is going to decrease to 0.5, so that's your P2, that's your second pressure. And they want to know what is the final volume going to be, so we're looking for the V2. So if you notice that the pressure went from 1 down to 0.5, since it decreased, your volume should increase because they're inversely or indirectly related. So here's the equation, and here's the variables that they gave you in the problem. And then all you have to do is plug it in and solve for it. So I rearranged the equation to solve for V2. All you have to do is divide both sides by P2. Plug in everything and make sure units match. So we've got ATM and ATM, so that matches. And then your final volume will match what your other volume was. So since we're in milliliters here, your final volume will be in milliliters over here. And just check and make sure it makes sense. So if pressure went from 1 to 0.5, it was cut in half. The inverse of a half is to multiply it by 2. So 500 times 2 is 1,000, so that makes sense. The next one we're going to keep constant is pressure. So at constant pressure, the temperature is going to be directly related to the volume. Which kind of makes sense. If you picture pressure as being the collisions of the particles with the container, if you have a balloon and you need to keep the number of collisions of those gas particles with the balloon constant, so the number of collisions needs to stay the same. If you start to increase the volume and make the balloon a whole lot bigger, in order to keep the collisions the same, you'd have to speed up those particles. And by speeding them, you're changing the temperature. Because remember, temperature is the average motion of the particles. So these two are directly related. And in this case, you have to use Kelvin. And the reason is because you can't ever put a 0 on the bottom of a fraction. It's impossible. So if we were using Celsius, there is a possibility we could get a 0 degrees Celsius. But for Kelvin, since 0 degrees Kelvin is absolute 0, and we've never actually reached absolute 0, so we can use Kelvin and not have to worry about that. The problem is, in the question, you're going to get Celsius because that's what our thermometers are in. So as soon as you see Celsius for this chapter, go ahead and cross it off, add 273, and rewrite it as Kelvin, and that way you won't forget. So here's our new problem. Let's go ahead and label everything. First of all, it says at constant pressure, which tells us we can use this equation. 2.75 liters tells us volume, so put a V1 on top of that. Says that it's at 20 degrees Celsius. As soon as you see that, go ahead and cross it off, add 273, and next to it I would write 293 Kelvin, and label that as your T1. That's your initial temperature. The temperature is going to change so that we get a new volume. So this is our V2. We want to know what would that new temperature be. So these are our variables. We've got our initial volume and our final volume. We have the initial temperature, don't forget to make it Kelvin, and we're looking for that final temperature. So here's the equation. You just have to plug in everything and solve for T2. Now, a lot of people have trouble solving for a fraction, so if you're one of those people who have really a hard time solving for fractions, to get rid of it, you can just cross multiply. So you would do 1.87 times 293 equals 2.75 times T2, and solve for it that way. And then always check and make sure your answer makes sense. Notice that our volume went down, and since volume is directly related to temperature, your temperature should also drop. So we started at 293, we ended at 199, so that makes sense. And the last relationship we're going to do today is constant volume. So if volume is held constant, the pressure and the temperature are going to be directly related. And that should make sense as well. If we have a balloon that cannot change the size, so the balloon is set in stone, it can't change what size it is. If you increase the temperature, so those particles are moving faster and faster and faster, the pressure inside that container is also going to increase. So since they do the same thing, we call it a direct relationship. If temperature increases, pressure also increases, or vice versa. If temperature decreases, pressure would also decrease. And again, anytime you use temperature for this chapter, make sure you convert it to Kelvin first. So P1 over T1 equals P2 over T2. Same thing as before, we're going to label everything, and then you just have to plug it in and solve for the variables. So we've got 1.8 atm, that's your initial pressure, so on top of that put a P1. And I see degrees Celsius, so as soon as you see that, I would cross it off, add 273, and you should get 296 Kelvin, that's your T1. We're going to get a new pressure, so now we have 2.5 atm. And assuming the volume doesn't change, that tells us we can use this equation. What is the new temperature? So these are our variables. We've got an initial pressure and a final pressure. We have an initial temperature, and we're looking for that final temperature. So here's the equation. Plug in your variables. And again, if you have trouble with the fractions, you can cross multiply. So 1.8 times T2 equals 296 times 2.5. And let's see what should happen to our temperature. Pressure went up, so temperature should also go up. So it should be a number higher than 296. And if you calculate it correctly, you should have gotten about 411. For these practice problems, if you take a look at worksheets 3, 4, and 5, each worksheet has a different equation that you can practice using. So I want you to spend some time working on those problems, and all the answers should be on there, so make sure you check your answers as you go. Worksheets 3, 4, and 5. And that is all.